This is 1961, IMO problem number 1. Here is a view of this problem. We're given a system of equations and we would like to solve for x, y, and z in terms of the parameters a and b. Notice that the third expression is slightly different than the other two. Well, the first and the second equation, by the way, look pretty symmetric as well. Also, the question requests from us to find the conditions on A and B that would make our solutions x, y, and z distinct positive numbers, positive real numbers. So we want to find x, y, z in terms x, y, z greater than 0, and in terms of A, B, C. AB, sorry for that, in terms of A and B. So let's start by making a small substitution. We can immediately get rid of the z in both equations, and so because this expression is kind of almost redundant looking, so let me go ahead and do that. So it's very easy to substitute the z square into the third expression, so which we get into the second middle equation, which we get x squared plus y squared. Z squared is just xy, and that's equal to b squared. But it's a little bit harder to do it in the first expression. So obviously either I would need to introduce as a square root xy here, or if I don't want, I can square this expression. But when I square it, there will be a lot of additional terms coming up, right? So therefore, before I square it, I will rewrite it in the following way. Let's just leave z on its own, and let's just write this as a minus x plus y. And now I can square it. So when I square this expression, I would get z squared on the left side, but z squared is just xy, so I can just substitute xy here. And when I square this term, the right hand side, I'll get a square plus, well, x plus y square, which is just x squared plus y squared. Let's move a little bit, plus 2xy, and then I need 2 times, minus 2 times a x plus y. And notice that everything is in terms of xy and the parameter a. So that's pretty good. We can further simplify things. For instance, let me change color actually. We just realized that this xy and the 2 here will cancel. And that's it. Now I can combine these two expressions. So we have this one and this one now. That's pretty good. We reduced it to two equations in terms of x and y, so we need to solve it for x and y from here. Let's go ahead and probably use our substitution. And when I do so, I need to be careful here. Yeah, it looks like I can just substitute here. So this expression x squared plus y squared plus xy, look at this, x squared plus y squared plus xy here. So this thing here is just b squared. So therefore our expression, so if I move this term to the left hand side and isolate the x plus y, I have a very nice result here. X plus y comes out as, well, a square plus b square all divided by 2a. I hope I didn't mess up the algebra. And then look at right. We can also look at this expression here. Look at this expression. Here I can replace x plus y with what I just got here. So therefore, and I can replace z with x. Right, I can do that in the second step. Okay, let's do it in slowly. Okay, so take this expression, right? So we start with that. Let's write it here. I would have, let's do it here. So z is equal to a minus, so x plus y I replace with this expression here, a squared plus b squared all divided by 2a. We can find the common denominator here, and well, which is obviously 2a. and let's do it. So I would have 2a squared here minus a squared. It will be just a squared minus b squared. I would get a squared minus b squared all divided by 2a. Now I can go ahead and square this expression, right? Square our expression, both sides. Z squared is just xy, so therefore this would imply that, curiously, x times y, and now you know where I'm going from here, right? Is just the square of this guy. So it's just the square of the numerator, which is a square minus b square square, and the square of the denominator, which is 4a square. Now, how to solve this system of equations? Well, there's multiple ways we can do, but one standard trick is to set up a quadratic. So therefore, x and y solve the following, the following quadratic equation. Following quadratic equation, which is really u square minus the sum a square plus b square all divided by 2a u, and then the product plus a square minus b square square over 4a square is equal to 0. So x and y are the two roots, well, the u, you can call them as u sub 1 and u sub 2 of the two roots that solves this quadratic equation. Now we can start the careful work. We need to figure out the conditions, right, on a and b that would make x, y, and z distinct. Oh, by the way, this is a good enough algorithm, right? Obviously, it's easy to solve this one for x and y. Once you know x and y, you can substitute and you can find z. But let's see. We don't want any imaginary root. We want x, y, z to be distinct positive. So that's important. The question reads distinct positive numbers. Okay, so let's be careful on this then. Okay, so how do we do it? Well, let's be very careful on the conditions. So let's do it step by step. Let's start with z first. So this is our expression for z, this parametrization for z. We want z to be greater than 0. That one won't lead anything so far. Oh, okay, let's have a look at this one. X plus y, because x and y and z all three are greater than 0, so this guy has to be greater than 0. Look at the numerator. That's positive, so therefore denominator must be positive. So from here, so far I know, so let's make note of this here in this box. So a has got to be greater than 0. Now going back to the initial thing that I got here, so this guy is greater than 0. We need z to be greater than 0, right? So therefore, hey, this thing has to be greater than 0. So that means a square has got to be greater than b square. So that's pretty cool too. And what else? So far I have found two conditions that are useful. And finally, well, x and y are positive real numbers, right? So reals. Positive numbers means real numbers, right? And they are distinct. So therefore, finally, I can focus on the, let me see. I can focus on the discriminant here, right? So I can focus on the discriminant. So therefore, we want the discriminant to be greater than 0 as well, because this is only the only way we can have two real roots, right? I just noticed that I could have found this result. The way I found it was from here. I could have found it easily from this too. But anyhow. Okay. So what is the discriminant? Going back to the discriminant, we have to have the discriminant positive. Why again? Because the discriminant of this quadratic will give us, and the two roots should be real and positive. So let's focus on the discriminant. Now this is a little bit bashy at this step, I guess. So we would have, well, obviously discriminant can't be equal to 0 because then it won't be distinct. We want distinct, so strictly greater. Okay, good. So it's just this one square, a square plus b square over 2a square minus 4 times this animal here. Let's just leave it as it is, a square of minus b square square over 4a square. Okay, this part is the part where I will do a little bit calculation here. I do a lot of silly mistakes in my videos, as you know. You might think I'm doing it on purpose, huh? Well, I'm not. But hopefully this time I won't make any silly mistake. I tried it previously, so the best way to handle this is the following. We have the common denominator here. Let's find the common denominator will be definitely 4a square. I'll just leave the 4a square here. So therefore here on this one we will have a square plus b square square minus and then I can make it this part here like a square a also, so 2 times a square minus b square close parenthesis square. Hey, why would I do that? Because this is a difference of squares, so I can easily manipulate this. So it would lead us to a square plus b square minus 2a square minus b square, or a square plus b square plus 2a square minus b square, all divided by 4a square. And just the last step, hopefully we have the 4a square, and so this one would give me there will be 3b square, right, so it will be 3b square here minus a square, and from the second one I'll have 3a square minus, okay, I'll have 3a square and minus b square. Okay, so we want this expression, remember, being greater than 0. Obviously the denominator is strictly greater than 0. Let's investigate the two terms on the numerator. Do I know anything about those? Of course I do. Look at that. Earlier I have found that a square is greater than b square. So that would mean that, and a and b are positive, so a square is greater than b square. Of course, this guy, it would mean that 3a square minus b square. So this one means a square minus b square is greater than 0. So this thing would be 2a square plus a square minus b square. Obviously this is greater than 0 as told earlier. This one is, so this whole thing is greater than 0. Perfect. So we know that this second guy is greater than 0, the denominator greater, so we must have this one. So this is our third condition, really. So we must have, if we want 3 distinct positive roots, 3b square be greater than a square. Now we can, that's it. Looks like these are all the conditions I need, right? So therefore, combining these 3 conditions, so I can write these 3 conditions would be, we are squeezing the a square between, well, a square is squeezed between b square here, but at the same time it's also less than 3b square. Or if you will, we can take the square root and we can further express it. You can further express it like this, I guess. So a well, b can be, hold on, a is greater than 0. Yeah, I don't have a restriction on b, so b can be negative apparently, right? So I'm not sure on that one. I think, okay, so I'm not sure, so that's why I might have to put, I know a is positive, but I might have to put yeah, that those absolute value terms here. So I want this thing to hold. That's it. And when that happens, life is very easy. Assuming, so we can easily calculate this positive discriminant. So the 2 roots that we will get, so therefore x and y would simply be equal to, so they would be equal to the 2 roots by the quadratic formula minus b, which is just this one, minus this, which is a square plus b square, all divided by 2a. minus b, oh, divided by further 2, sorry for that, so therefore 4a. Remember from the oh, come on. Okay, so this one is a 4, so this one is a 4, and plus or minus, okay, I won't bother calculating the discriminant, which is this very ugly thing, so you just plug it in here, obviously. So the discriminant divided by 2 also, that's it. So once you find the x and y, it would imply that z is just, remember that z squared is xy, so z is just square root of xy, the geometric mean. And notice here that because the discriminant is positive, x and y would be distinct. When x and y is distinct, of course the geometric mean would also be distinct, right? So we will get a further distinct number here, but earlier we have found a parametrization for that, so I'll just go back to that earlier result somewhere. Oh, here, somewhere here, a square minus b square over 2a. That's it. A square minus b square over 2a. And I know this thing is also positive. Okay, so that solves this problem. Well, you can significantly simplify the algebra, noticing that this thing, they are symmetric polynomials. There is other ways to handle the algebra, obviously, using you could have set up a cubic at the beginning, a cubic expression at the beginning, and then so these are useful to find the coefficients of that cubic polynomial. I'll just leave it to you as an exercise, but in fact I want to mention one interpretation of this. We could have interpreted this in three-dimensional space. What would be this thing? The first one is a plane, right? It's a plane on 3D. In fact, right, so one way to okay, so this one is a plane, let me at least mention that, and this one is just a circle on 3D. Well, not a circle, what do you call it? A sphere, I should say, sorry, not a circle, a sphere. So this one is a little bit harder to visualize, but it is well, it's if you will, if you consider this as the x and y axis, so it would be like a shape which keeps increasing, like so it's on the third dimension, right? So these are level curves, z1, z2, z3, z4, z5, where each of these levels are increasing, right? So the reason I said that is because this trivializes this condition, right? So where's our condition here? This condition is trivial with this geometric interpretation. Let me quickly tell you why. So we had these, let's put it here, and then we can finish the video afterwards. So x plus y plus z is equal to a. Well, that's simply the simplex, right? So it's just, if you have the x, y, and this is the z, so this is an a here, a, and a here. So you have this plane which cuts it through here. I'm not interested in the other parts of the plane, right? Does that make sense? I'm only interested in the part where x, y, z are positive, which is just this portion, which turns out to be an equilateral triangle, right? With side length a root 2, sorry for that. How about the other one, the other condition, that x squared plus y squared plus z squared equals b squared? Let's write that down too, and let's plot it on the same picture. Is equal to b squared. So this is a sphere centered at the origin here. So that's when you draw it. So you can draw the sphere. The sphere will eventually, you want it to intersect with this plane, right? So therefore, it will be as if you will have this circle intersection between the two, if the sphere is large enough. So what is the distance of this plane to the origin, right? So it's very easy to calculate that. Obviously, you can calculate it in multiple ways. One way to focus to figure it is to just intersect the you can make a volume calculation, if you will, and then you can calculate the height of that pyramid, if you will. But alternatively, what you can do is you can focus on this line, x equals y equals z, and you would intersect it with our plane, which was this. When you intersect them, you just realize that they intersect at this point. So therefore, well, this is the coordinates. A over 3, B over 3, C over 3 is where the projection of the origin onto this plane, right? So it would be this point, and it's very easy to calculate the distance of this point to the origin, 0, 0, 0. The distance turns out to be what? A over root 3, I guess, right? So you can easily use the distance formula in 3D, so you would get a distance like this, and it explains it, right? So because the distance of this plane to the origin is this much, you want the your sphere to have a radius b. So the radius of that sphere is b, obviously. You want the radius to be at least as big as this. Whenever that's the case, we will have this circle intersection between the sphere and this plane, so they will intersect like this. However, you don't want the radius this b to be too big. Why? Because if it comes bigger than this one, right? So if it becomes bigger than a, does that make sense? If b becomes bigger than a, so this is the limit on the b. You want the b to be strictly less than a for sure. Well, when you look at these and you just recognize, hey, we have observed this earlier, right? So because the sphere, otherwise it will be beyond, it will still touch. I mean, it will not touch the plane, at least this triangle region of the plane here, right? So it will touch the plane on the other side, which will have negative solutions. So that and that's it. That solves our problem one more time. It gives us the same conditions that we need so that the roots can be distinct and real positive numbers. And that solves our problem. So this 1961 IMO problem number 1. Hope you enjoyed the video, and looking forward to see you guys in our next lecture.